Welcome back to the Deep Dive. Today we are conducting a rigorous analysis of a paper that effectively redefines the architectural standards for open-set object detection.
It really does. It's a massive shift.
We are dissecting grounding DINO, marrying DINO with grounded pre-training for open-set object detection. This is by Shilong Liu and colleagues. And this work is not merely an incremental improvement on metrics. It represents a fundamental shift in how we architect neural networks to fuse vision and language modalities.
It is excellent to be here, and you're absolutely right. This paper is significant because it tackles the tight fusion problem head-on. If you have been following the evolution of detection, from the early days of RCNN through the YOLO variations and finally to the transformer-based DETR revolution.
The ETR models really changed the landscape.
Exactly. But if you look closely, you know that the integration of natural language has often been a secondary consideration, a bolt-on feature, if you will. Grounding DINO changes that paradigm entirely. It proposes a deeply integrated dual encoder, single decoder architecture that allows language to guide the detection process from the feature level all the way to the final box prediction.
Precisely. And before we get into the tensor level operations, let's frame the problem space for you. We are moving from closed-set object detection to open-set object detection. In the closed-set world, which basically defined the last decade of computer vision, we were bound by fixed ontologies.
Right.
You train on COCO, you get an output vector of size 80. You train on objects 365, you get 365. The model is essentially a classifier operating on a fixed discrete distribution.
Yeah, and the limitation there is obvious, generalization.
Right.
If you encounter an object that wasn't in your training set's category list, say a specific type of industrial valve or a biohazard suit, the model is structurally incapable of identifying it.
Just maps it to background.
Exactly, or it hallucinates a known class that looks somewhat similar. Open-set object detection, or OSODE, flips this completely. The input is not a class index, it is a natural language description. The model must map the semantic space of language to the spatial space of the image.
And the mission of this deep dive today is to understand the specific engineering choices that allow grounding DINO to do this with such high fidelity. We are going to deconstruct the architecture into its three critical phases. That's the feature enhancer, which acts as the neck, the language-guided query selection, and the cross-modality decoder, the head.
We should also state up front why we are focusing on this specific paper. The results are non-trivial. Grounding DINO achieves a 52.5 average precision, or AP, on the COCO zero-shot benchmark.
Which is...
For our listeners who live in these benchmarks, that number is staggering.
It really is. It rivals fully supervised models like faster RCNN trained on COCO, despite grounding DINO never having seen a COCO image during training.
Yeah, it also sets a new state-of-the-art on ODIN-W, object detection in the wild.
That zero-shot capability is basically the acid test for AGI-adjacent systems. Proficiency in handling open-world scenarios. So let's start with the foundation. The authors chose DINO as their base detector. For clarity, DINO here stands for DETR, with improved denoising anchor boxes.
Yay.
Why DINO? Why not build this on a CNN-based architecture like Efficient Det or a standard ResNet FPN setup?
It comes down to the homogeneity of the architecture. Classical detectors are highly heterogeneous. Take faster RCNN. You have convolutional backbone, a region proposal network, an ROI align layer, and then fully connected heads.
Right, lots of discrete, rigid blocks.
Exactly. These components operate on totally different representations. Injecting a continuous language signal into that fragmented pipeline is mathematically awkward. You usually end up with what we call shallow fusion, where you only combine vision and language at the very end.
Essentially just performing dot products between the final box features and the text embeddings.
Precisely. Which is insufficient because the vision model hasn't been conditioned by the language during the feature extraction phase. It has already discarded irrelevant features before the language has a chance to say, hey, wait, I actually care about that specific texture or shape.
DINO, being a transformer-based detector, is uniform. It is attention layers all the way down.
Yes. And this allows for what the authors call tight modality fusion. They can inject language features at the backbone level, the neck level, and the head level because the data structures, the tokens, and embeddings are entirely compatible throughout the network.
Let's visualize the high-level topology before we zoom in.
Yeah.
We have a dual encoder setup.
Correct. On the visual side, they utilize a SWIN transformer. They experiment with SWIN-T, the tiny version, and SWIN-L, the large. This backbone extracts hierarchical visual features. Let's define the output of this visual backbone as a set of multi-scale image features.
And on the language side?
They employ a BERT-based model. It takes the text prompt, whether it's a simple noun phrase or a really complex sentence, and outputs a sequence of text tokens. We can call that N sub T tokens, typically with a maximum length of 256.
So at time t equals 0, we have raw image features and raw text features. They are effectively in different latent spaces. The first step of deep fusion happens in the neck, which they call the feature enhancer.
This is a critical divergence from standard object detection. Usually the neck is a feature pyramid network or a path aggregation network, which simply handles multi-scale resolution mixing. In grounding Dino, the feature enhancer is a stack of transformer encoder layers designed explicitly to force these two modalities to interact.
Let's drill down into the operations within a single layer of this feature enhancer. It's not just a standard self-attention block.
No, not at all. It's a specific sequence of 3 attention mechanisms. First, you have self-attention on the image features. This is standard. It allows the image tokens to refine their representation based on global or local visual context. But immediately following that, we have text-to-image cross-attention.
Let's define the query's keys and values for that specific operation. For our listeners working with attention matrices every day, how does this map out?
In text-to-image cross-attention, the image features serve as the queries, while the text features serve as the keys and values. Mathematically, the model is calculating the attention weights between every visual token and every text token.
So if a visual token corresponds to a red car, and the text token is the word car,
The dot product there is high, and the visual token absorbs the semantic information from that text embedding.
this effectively paints the image features with language semantics. The image representation itself shifts in the latent space to emphasize regions mentioned in the text.
Exactly. It's brilliant, but they don't stop there. The next sublayer is image-to-text cross-attention. They flip the roles. Now, the text features are the queries, and the image features are the keys and values.
Why is this bidirectionality necessary? Doesn't the first cross-attention pass give us what we need for detection?
You'd think so, but no, because language is polysemous and heavily context-dependent. Think about the word bank. It has a completely different embedding vector, depending on whether it appears in the context of a river or money. By allowing the text to attend to the image, the model can disambiguate the text prompt based on visual evidence.
Right. So if the prompt is the word bat and the image contains a baseball field, the text embedding for bat aligns itself with the sports equipment, not the animal.
Exactly. This yields fully contextualized representations for both modalities. The text knows about the image, and the image knows about the text.
I noticed a specific implementation detail regarding the image attention in this phase. They employ deformable self-attention, specifically for the image features. Why distinct this from vanilla global attention?
That is a pure computational necessity. Visual feature maps, even at the neck level where they are slightly downsampled, are high-dimensional. We are talking about thousands of tokens, let's say N sub I tokens. Vanilla self-attention scales quadratically, right? Big O of N squared.
Yeah, computing that attention matrix becomes a massive bottleneck.
Exactly. If you have 10,000 tokens, you are computing a 100 million entry attention matrix. That is prohibitively expensive for both training memory and inference latency.
So deformable attention reduces this complexity.
Yes, it was introduced in the deformable DEPR paper. It restricts each query to attend only to a small set of learned sampling points around a reference point, usually using bilinear interpolation to sample the exact feature values. This makes the complexity linear, big O of N.
Which allows the feature enhancer to process high-resolution feature maps without exploding your GPU memory.
Exactly. It's a crucial engineering choice to make tight fusion viable at scale.
Okay, so leaving the feature enhancer, we have cross-modality text and image features. Now we face the initialization problem. In the original DETR, object queries were learned parameters. They were static vectors that didn't know anything about the specific input image.
Correct. Those static queries were essentially learning spatial priors from the training set, like objects tend to be in the center or small objects tend to be clustered. Dino improved this by initializing queries based on the output of the encoder, selecting salient regions.
But salience in standard Dino is purely visual. It just picks out foreground objects.
Which is highly problematic for open-set detection. If I ask the model for the background tree, but the visual saliency highlights the foreground person, the model might fail to even generate a candidate box for the tree.
Because the queries are entirely initialized on the wrong parts of the feature map.
Right, and this brings us to section 3 of the paper, language-guided query selection. This acts as the bridge. It is arguably the most elegant component of the entire architecture. Instead of relying on generic visual saliency, they use the fused features to select queries that are specifically relevant to the prompt.
Let's break down how this is mathematically formulated.
They take the output of the feature enhancer. Let's call the image features x sub I and the text features x sub t. They calculate the dot product similarity between them. This generates a logit map. It is essentially a heat map of where the image matches the text conceptually.
So if the prompt is zebra, the heat map spikes at the exact pixel locations of the zebra in the multi-scale feature map.
Precisely. They then select the indices of the top n sub q features based on those logit scores. They default to 900 queries in this specific implementation. These indices determine the initial bounding boxes, the reference points, and the content features for the decoder.
This means the decoder is not starting at search from scratch or from a random distribution of spatial priors. It is starting with 900 hypotheses that are already highly correlated with the user's specific text request.
Yes. It acts as a massive coherent prior. It bridges the gap between the fused features and the detection head. It ensures that the head is looking in the right places from layer 1. You aren't wasting decoder layers just trying to find the general vicinity of the target.
Let's move to that head. Section 4, the cross-modality decoder. We have our 900 language-guided queries. They enter a 6-layer transformer decoder stack.
Now, in a standard Dino decoder, each layer has a self-attention mechanism. That's where queries attend to each other to perform tasks like duplicate removal, functioning somewhat like a soft non-maximum suppression. And it has an image cross-attention mechanism, where queries probe the image map using deformable attention to refine their box coordinates.
Standard DETR stuff so far.
Right. But grounding Dino inserts a crucial third component into every single decoder layer: text cross-attention.
This seems to be the enforcement mechanism of the whole architecture.
That is a perfect way to put it. In the text cross-attention layer, the object queries, acting as Q, attend to the text features, which are K and V. This allows the model to continuously realign its box refinement with the semantic instruction.
Why is this continuous alignment necessary, though? Why isn't the initialization from the bridge phase enough? We already seeded the queries at the location of the zebra.
Because the decoder layers are highly iterative. As the query moves through the 6 layers, it is refining the bounding box coordinates and updating its content vector through a feed-forward network. Without the text cross-attention, the query might drift.
Drift visually.
Exactly. It might lock onto a visually dominant feature that is adjacent to the target but semantically irrelevant. Say you want the saddle on a horse. The initialization might hit the saddle, but as the query refines its box, the visually dominant horse features might pull the bounding box to encompass the whole horse.
Oh, I see.
The text cross-attention acts as a semantic regularizer. It constantly reminds the query, remember, you are looking for the saddle, not the horse.
And the output of this decoder stack gives us our refined boxes and extracted phrases. They use a contrastive loss here, right, as the classification signal.
Yes, instead of a standard cross-entropy loss over a fixed set of classes, they use contrastive alignment between the final query features and the text token features. They want the dot product of the matched region and its corresponding text token to be maximized, while pushing away non-matching tokens.
The ablation studies in the paper strongly support the necessity of this tight fusion. Removing the text cross-attention from the decoder resulted in a significant drop in AP.
It confirms the tight fusion thesis unequivocally. You cannot just fuse at the beginning. You must fuse throughout the computation graph. Every single phase, neck, bridge, and head needs access to both modalities.
So we've discussed the architecture extensively. Now we must address the learning component. Section 5, training strategies and data handling. An architecture is really only as good as the signal it propagates during backpropagation.
And they adopted a very specific and clever data strategy. They trained on a combination of data sets: standard object detection data, specifically Objects 365, grounding data using GoldG, and caption data.
Caption data is particularly interesting because it lacks bounding boxes entirely. It's just an image and a sentence, like a cat sitting on a mat. How do they derive a dense training signal from that for an object detector?
The paper highlights a specific technique called sub-sentence level representation, which is vital for handling complex text inputs.
Walk us through that parsing process.
If you feed the sentence, a cat sitting on a mat, into the model, a naive approach treats the whole sentence as a single global label. But grounding Dino parses the sentence to extract positive noun phrases. It identifies cat and mat as distinct entities. It effectively turns one caption into multiple distinct detection tasks.
It forces the model to learn fine-grained localization. It's not enough to just know the image globally contains a cat and a mat. The model must spatially distinguish them and assign separate bounding boxes.
Correct. And to unify the training across detection datasets, which typically just have lists of classes, and grounding datasets, which have natural sentences, they use a technique called concatenated prompts.
This solves the referring expression comprehension versus standard detection dichotomy.
Exactly. Referring expression comprehension, or REC, targets a specific object based on a complex description, like find the man in the red shirt on the left. Detection targets many objects from a predefined ontology. Find all people, find all cars. To train on a detection dataset like COCO, which has 80 classes, they don't run the model 80 separate times.
That would be incredibly inefficient.
Right. Instead, they concatenate the class names, person.bicycle.car.motorcycle, and so on, into a single long text sequence.
So the model treats the list of discrete classes as a really long, grammatically disjointed sentence.
Yes. And because of the attention mechanisms we described earlier, specifically the bidirectional cross-attention in the neck, the model can attend to the person token and find all people, and simultaneously attend to the car token and find all cars. This unifies the mathematical formulation of REC and standard detection. The model doesn't care if the prompt is a fluent sentence or a concatenated list of nouns.
That is a very elegant way to unify the loss functions across wildly different dataset formats. Let's look at the empirical evidence. Section 6, Experiments and Results. We already mentioned the 52.5 AP on COCO Minival in a zero-shot setting, which is the acid test here.
To contextualize that for the audience, the original Dino model, when trained on COCO, gets around 63 AP. Achieving 52.5 without ever seeing the COCO training distribution is remarkably close. It proves that the model isn't just memorizing COCO statistics. It suggests that the semantic features learned from O365 and Golgi transfer exceptionally well when they are anchored by a robust language prior.
But the more revealing result, at least in my opinion, is on the ODIN-W benchmark, Object Detection in the Wild. This is a suite of 35 diverse datasets, everything from thermal imaging to microscopic cell counting to aerial photography.
Grounding Dino set a new record here with a mean AP of 26.1. But the specific comparison between model sizes is what provides the real deep insight for network designers. They compared a Grounding Dino model equipped with a SwinTiny backbone against a standard Dino model using a SwinLarge backbone.
And the SwinTiny is significantly smaller. We're talking about a fraction of the parameter count and FLOP pieces compared to the SwinLarge.
Yes, drastically smaller. And yet, the SwinTiny Grounding Dino outperformed the SwinLarge standard Dino in full-shot settings on this benchmark.
Let's pause on the implication of that for a second. A smaller visual backbone, when augmented with deep language understanding, beats a much larger visual backbone that relies on vision alone.
It suggests that language is a remarkably strong prior. The semantic embedding provided by the BERT encoder resolves visual ambiguities that would otherwise require a massive visual cortex to parse. If the model knows it is looking for a stop sign, it doesn't need as much raw visual processing power to distinguish the red octagon shape from a background red blob.
The language effectively narrows the search space in the high-dimensional manifold.
Precisely. It guides the visual features toward the correct subspace much faster than purely visual hierarchical feature extraction.
This has profound efficiency implications for the field. It suggests that for edge deployment, where compute and memory are strictly bounded, we might be better off fusing a small vision model with a language model, rather than just endlessly trying to scale up the CNN or vision transformer.
I agree completely. It validates the multimodal approach as a legitimate path to computational efficiency, not just a way to add new capabilities.
They also evaluated on referring expression comprehension specifically. Datasets like RefCOCO, RefCOCO Plus, and RefCOCO G.
Here the task is pure disambiguation. The prompt is the man on the left, not just a man. Grounding Dino outperforms GLIP here, GLIP being grounded language image pre-training, an earlier state-of-the-art model. The key takeaway in the REC evaluation was the fine-tuning delta.
The difference between zero-shot and full-shot.
Right. The zero-shot performance was very strong, but adding specific REC training data yielded a massive jump in AP. This indicates the architecture is highly plastic. It generalizes well out of the box, but can also specialize rapidly given domain-specific syntax and spatial constraints. Most open-set detectors fail completely at REC without specific fine-tuning, but Grounding Dino showed robust baseline zero-shot metrics.
We should also touch briefly on the ablation studies.
Yep.
I mentioned the decoder text attention ablation earlier, proving tight fusion. Were there other critical findings in the ablations that stood out to you?
The comparison of query initialization methods was stark and really validates their design. They compared three setups: random queries, which is the baseline DETR approach, image-guided queries, which is standard Dino, and language-guided queries, their novel contribution. The language-guided approach yielded a gain of several AP points.
It empirically proves that the bridge phase, filtering features based on the prompt before the decoder, is practically non-negotiable for high-performance open set detection.
Absolutely. Moving to Section 7, Applications and Extensions. The paper goes out of its way to demonstrate that grounding Dino is not just a discriminator, it's a facilitator for generative AI.
This is where the work becomes part of a much larger ecosystem. They showcased integration with Stable Diffusion for image editing.
Yes, this is the classic in-painting workflow. Typically, in-painting requires a user to manually draw a mask over the object they want to change. It's tedious. Grounding Dino automates this entirely.
So a user prompts, change the dog to a cat.
Exactly. Grounding Dino takes the dog part of the prompt, detects the dog in the image, generates a high-precision bounding box, and creates a segmentation mask. This mask is then fed into Stable Diffusion along with the new prompt, cat.
It effectively closes the loop. Text to box via grounding Dino plus box to image via Stable Diffusion equals fully automated text-based image editing.
They also demonstrated integration with Gilligan, grounded language to image generation. Gilligan is a generative model that accepts bounding boxes as layout constraints. Grounding Dino can read the layout of a source image, extracting bounding boxes for all the detected objects.
And those layout coordinates are passed to Gilligan.
Right. Gilligan then generates an entirely new scene with the exact same composition.
It essentially allows for complex semantic style transfer, where the underlying geometry and spatial relationships are perfectly preserved via the detection boxes.
It positions grounding Dino as a vital middleware layer in the modern generative stack, translating between raw pixel space and semantic layout space.
We have covered a tremendous amount of ground today. Let's synthesize the core contributions for you. Grounding Dino successfully marries the transformer-based detection architecture with grounded pre-training. It validates the tight fusion hypothesis.
It proves that cross-modality attention must be ubiquitous in the neck, the initialization, and the head to achieve state-of-the-art open set detection. And it does so while maintaining a clean, transformer-native architecture. It completely avoids the mathematical heterogeneity of previous classical approaches.
However, we must address the technical limitations. The authors themselves acknowledge the issue of hallucinations, which is a known failure mode for these systems.
This is a persistent issue in vision language models. Because the language prior is so computationally strong in this architecture, it can literally override visual evidence.
So if you prompt the model to find a unicorn,
the attention mechanisms might force the visual features of a horse to artificially align with the unicorn text embedding. The model detects an object that simply isn't there or misclassifies it purely because the text heavily biased the search space.
this suggests a really tricky trade-off. The exact same mechanism that helps the model find a small, obscured stop sign in a busy intersection, that strong prior, also causes it to hallucinate objects in pure noise.
Exactly. The sensitivity of the language-guided query selection means the model is biased toward finding something that matches the query, even if the confidence is low. Calibration, teaching the model to confidently output nothing found, remains a very active area of research.
Additionally, there is the inference cost. While the tiny backbone is efficient relative to a large SWIN, running a BERT encoder and a SWIN transformer in parallel, plus all those multi-layer cross-attention matrices, is not computationally trivial compared to a closed-set YOLO model.
Very true. For real-time applications at 60 frames per second on edge hardware, this architecture might still be too heavy. It is currently much more suited for offline analysis, complex video indexing, or as a component in a larger generative pipeline where latency is less critical than deep semantic understanding.
To conclude, Grounding Dino represents a true maturation of the field. We are officially leaving the era of the 80 classes and entering the era of free-form description. The ontology is no longer hard-coded into the final classification layer. It is dynamic, defined at runtime by the user's natural language.
The dictionary is the new dataset, and the multimodal transformer is the universal translator between that dictionary and the raw pixels.
That is the defining takeaway. Thank you for this rigorous breakdown. It is a dense paper, but the architectural elegance, once you get past the dense notation and matrix math, is undeniable.
My pleasure. It is a pivotal piece of work that will influence architectures for years.
For our listeners, we leave you with this final technical consideration, something to mull over. If the model's spatial reasoning and detection performance is now inherently bounded by the quality of the language embedding, currently BERT-based, what happens when we swap BERT for a true large language model like Llama or GPT-4? Does the detection capability scale linearly with the reasoning capability of the text encoder? That is the next frontier of type fusion. We will see you in the next deep dive.